Alright, greetings class. Today we are going to be talking about the difference between real gases and ideal gases. Okay? So please get your notebook out because we're going to jot down a few concepts or vocab words regarding these two topics. Okay, since we are talking about gas laws in this unit, it's important to note that for our formulas to work, okay, we need ideal gases. And these essentially are imaginary gases or an imaginary scenario or imaginary particles that work just perfect. Okay, so there are fancier formulas that talk about and calculating the properties of real gases, but for the purposes of this course, we're just going to be focusing on ideal gases. Okay, so it's essentially kind of working with these perfect scenarios so that our formulas can work. Okay, all right. So, without further ado, what would this class be without? Some simulations. Now, I pulled these up from Canvas and they'll be posted within the assignment, but I have two different tabs open and I want to talk about two different scenarios. I wonder if you can already decide which one do you think is the imaginary gas particle and which one is the real one. So, you probably could guess that this looks like a real molecule, and if you guessed water, you're correct. So I want to go to the ideal scenario of what a gas particle is. I'm going to hit play here, and I'm going to mark two atoms because it's easier for us to see. Okay, just kind of focus your gaze on these two dark purples circles. What's the direction in which they're going? Do they ever sit still? These are the kind of the questions that you should be kind of observing at the moment, okay? Now, let's go to a water molecule. This is a real gas, and as you can see, we have our thermometer over here, and I'm going to put, we have charges here, and I want to show this you guys in slow motion. Look what's happening in slow motion. Since this is a molecule of a gas particle of water, okay, so we have more than one atom. We are bouncing around, but there is some vibrating, and more importantly, what I really want you guys to focus on is these interactions. In the real world, gas particles interact with each other. And for our formulas to work, okay, we want limited interaction as possible. So I'm going to go back, and I'm also going to show you guys what happens if I change this thermometer over on the right-hand side. What happens if I remove the heat, because there is no such thing as cold. If I remove the heat, do these gas particles look anything like these? Now remember, the purple dots, all of these are purple dots, circles, in random motion, going in straight lines, bouncing off of each other. They are, doesn't appear that they're losing any energy or slowing down. And then let's compare and contrast over here. If I take the heat or remove the heat away, these don't really look like gas particles anymore. If they start coming together, in which they are, I think that's what we call condensation. So these gas particles are probably going to go into the liquid phase pretty soon, and then in the solid phase, as we call ice. So this, again, we're in the gas law chapter, and think about it. Do you think gas law formulas will work with liquids or solids? The answer is no. Okay, so we want to keep these in the gas phase. So in order for these water molecules to be ideal, or another way of putting it is in a perfect scenario, how do we get our water molecules look like this? We are going to crank up the heat. Here we go. All right, now we go. Now, it's not perfect, but in order to take a real gas in the real world and have it apply to our formula, okay, we've got to make some assumptions. They're in random motion. They're not interacting. We're going to keep them in the gas phase. When they bounce off of each other, they're not going to stick and lose energy. Think of it like billiard balls on a pool table, okay? Random motion. They're ricocheting. That's what we call elastic. When they stick together and they lose energy, that's what we call inelastic collisions, okay? So let me pause that for just a second, and let's go back to our notes. Now that you kind of have a good mindset for what we... that's not it. It's right here. Our notepad. All right, so we have ideal versus real gases. Now, let me get my pen out. Perfect. Red pen. Ideal gases. Now, these are the purple ones that were bouncing around, okay? They fit perfectly in the kinetic molecular theory. So they fit within the KMT. Or another way of saying that is the kinetic molecular theory, okay? And we'll talk about that in a little bit. All right. They are tiny. Oh, they are tiny, okay? And they're far apart. Now remember, in a perfect world, we want these gas particles to be tiny and far apart. We do not want them to be close to each other and start condensing into the liquid phase or causing chemical reactions. Okay, so it's really important that we do not want chemical reactions from forming something else, losing energy in the form of heat, etc. However, if they are not far apart and they do come together, we want elastic collisions. Elastic collisions. Very important. We do not want any energy loss. So there's no kinetic energy lost. Okay? If they do come together and bounce off of each other, no kinetic energy is lost. Okay? Additionally, movement is random. Movement is random, constantly moving. So it's and constant. Okay? And that there's no attractive forces. We do not want any type of intermolecular forces. We do not want a chemical reaction to occur. We do not want ionic and covalent bonding between any other molecules. Nothing. Okay, so we just want them to all be independent of each other. And remember, this is the ideal scenario. These are just, we could almost say that these are imaginary because it's so perfect, okay? The last big thing, I'm going to change my pen for this because this is muy importante. The average kinetic energy, so I'm going to say average, AVG, kinetic energies, KE, the average kinetic energy is proportional, that's what proportional is, to temperature in kelvins. We're going to talk about what kelvins is in just a second, but the average kinetic energy is proportional to temperature, okay? Not the element. Not the element. Okay. So let me hold off for just a second and explain what that means. Let's go back to play. Now, temperature is off to the right, and it's important to just kind of look at the entire picture as a whole. You might notice that we are almost in a scenario in which they are behaving ideally, the gas particles, but they're not all moving at the same exact speed. Some are moving a little bit slower at times, and some are moving a little bit faster at times. They are ricocheting. We're not forming liquids or condensing into a different state or forming different molecules. But it's important to note that if we look at this entire page, the average between all of these molecules is proportional to, not exact, proportional to heat in kelvins. So temperature in kelvins. It is proportional to, kinetic energy is proportional to kinetic energy is proportional to temperature in kelvins. There we go. I got it. Now, if I start decreasing the temperature, what is that an indication of? Are they all moving at the same speed? No. Are some moving faster and some are moving slower? Yes. But as a whole, their kinetic energy is decreasing. Okay? Remember, kinetic is energy of movement. Okay? Again, temperature is proportional to kinetic energy. Okay? Temperature in kelvins. And that's what's going to bridge us to the next concept when we start talking about kinetic molecular theory. Okay? So as a wrap up, ideal gas particles fit within the kinetic molecular theory, which we're going to talk about next. They're tiny, they're really far apart, but what happens if they do collide? Well, if they collide, it's like a pool table, a billiard ball. They just bounce right off of each other. No kinetic energy is lost. Okay? The movement is completely random and constant. Remember, if the movement is not constant, then we're forming a different state, whether liquid or solid, or they're going to start coming together and they're going to start having attractive forces. So we want them to be moving fast, ricocheting, and no attractive forces. And remember, it's the average of all of the gas particles that we're focusing on is proportional to temperature in kelvins, not the element. And then you're probably wondering, what do we do over here, Mr. Murphy, for real gases? Well, simply put, it's the opposite of ideal. Okay? Opposite of ideal. Everything is the opposite on the right hand side. Okay? All right. Thank you so much, everybody.